Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. We're going to see a series of fluid mechanic experiments, starting with water films. And these are going to be water films that look like soap films, but they're made with pure water. And they're significantly thicker than a soap film. They're of the order of 300 microns thick, instead of just a micron or two thick, which you would find in a soap film. And the way you make these films is you stick a wire loop in a bag of water, and you pull the wire loop out, which we will shortly see how that happens. But you need to have some kind of equivalent to a zero gravity beaker. And what we will see here is how we can use a 4-inch square Ziploc baggie as a two-dimensional beaker in our weightless environment.
I fill in a small Ziploc up with water, and it makes a real handy way to handle an open container of water.
Now that you've got this beaker, which you can see if you squeeze it, the contact wetting angle forces keep the water contained in the beaker.
And there you see a little wire loop that I made from stainless steel safety wire.
And this loop is a 50 millimeter diameter loop.
So I'm going to stick this wire loop in the baggie, and there's no soap or anything in that water. It's just our pure drinking water. And you pull the wire loop out from the baggie, which makes that two-dimensional beaker, and lo and behold, you have a stretched thin film of nothing but water hanging onto your loop.
Here you can see a side view of the loop being withdrawn from the beaker. And right before the beaker is withdrawn from the loop, you could squeeze the beaker and inject a little extra water on it. And you can make films that are several millimeters thick. Or you can stick the bag back on and let the contact wetting angle forces suck most of the water off, and you'll be left with a film that's about 300 microns thick.
And you can see that the surface tension wants to make the film fairly thick. And this film there, as it's leaving, is probably 2 or 3 millimeters thick. And what you can do is you can stick the bag back on it, and you could use the curvature of the meniscus next to the bag to suck the water off. So it's of the order of a half a wire diameter. And that's what we have there for that particular film.
And here we can see some light reflecting off the film, and you can see some traces of wave motion left on the film.
And we've never seen anything like this before, where you can make a thin film of pure water, and it has some rather unusual properties, which you'll see here. It's thin. It's about half the thickness of the wire, and that's a 25 thousandths wire. It's thick enough that it doesn't exhibit the interference colors that soap bubble films do. Soap bubble films are a lot thinner.
These films make delightful oscillators, and here we're waving one of these films back and forth, and you can see the oscillations develop in the film.
But it's quite a tenacious film, as you can see there. It kind of acts like a rubber film or a drum head. You can sit there and shake the loop around, and you can collect these fairly large lenses of water induced from the flow, and it just sits there and hangs onto the film.
And because there's a fair amount of mass associated with this film, you get these wonderful lenses forming on each end of the film as it starts and stops in this oscillation. And every once in a while, a drop of water falls off of these films. And here's some digital still images showing what these water droplets look like as they go falling off of the films. And then we were fortunate enough to catch one of these films right in the middle of rupturing. And they're significantly thicker than a soap film. They're of the order of 300 microns thick. The contact wetting angle forces keep the water contained in the beaker.
And you could use the curvature of the meniscus next to the bag to suck the water off. And Houston Alpha, that's it for our Saturday morning science.